close to each other. So it's the number of people per unit area in a room that matters. Oh, wait, how many do we have now? 3, 4, 6, 8. No, we are still okay. Oh, just the right number. Actually, this weekend I spent the equivalent of the amount of time necessary to write a paper on this question of the virus and what to expect from it, because there is already a lot of data online about how many people got infected in different countries and so forth. And you can do a very simple calculation. You can fit all the existing data to an exponential. It fits very well. In all the countries, yeah, you can see. In all the countries, the rise is exponential. And so you get the time, the e-folding time, and you can ask, when will this curve reach a few billion people, at which point it will saturate, right? Because that's the number of people worldwide. Turns out that is the second week of May. Second week of May, plus or minus a week. So we're talking about 2 months, very difficult months, but I don't think anyone's sitting here. Absolutely.
This is also not being used.
More chairs.
Thanks. So we're talking about a couple of months or so, and obviously from the point of view of Harvard, the decision was that you cannot just let, you want to let the undergrads go because they sit in very closed quarters, the dorms, and that's like a petri dish. And it's quite likely that the virus is already on campus. So if you let them go for spring break, they better not come back. So that was the decision. And all the courses will be online. And gatherings of more than 25 people in a single room like this is forbidden. And most of the postdocs are encouraged not to participate in group meetings. They can work from home and interact by Zoom. So Harvard has this website where you can create your Zoom account. It's based on your password, the Harvard ID. So I encourage everyone to get there, so that, because we will have a lot of communications going through Zoom. These talks eventually will be on Zoom after spring breaks.
How do they decide the number of people that makes an unsafe room? Or?
Well, it's basically the likelihood. You want the likelihood of transmission to be small. Okay. The general goal of this exponential growth depends on a factor, which is by how much does a single person increase the number of infected people. Okay, and this ratio, if it's less than 1, then you suppress the spread, and if it's bigger than 1, so right now it's of order 2. Okay, and I can give you 2 examples. In Italy, there was a guy from the north that had a relative that passed away, and so he went to a funeral down in the south, and he didn't know, he didn't have the symptoms yet, but because it takes a week or so for the symptoms to develop. And so when he reached the funeral, a lot of people in the village came and hugged him, to show their condolences. So he infected 400 people in the village, and then the entire village was shut down. And now Italy is in complete lockdown. Now the one subtle point I should mention after looking into this, the one subtle point is you can't just fit an exponential curve in terms of, so if you have 1 dead person, let's say, out of this disease in a place, it means that this person got infected a few weeks earlier, let's say 3 weeks earlier, and if it's 1 in 100 chance, let's say 1% likelihood, which is the current statistics, 2% maybe of, and by the way, this fraction of people that die out of this depends very much on age. So at age 20, it's more like a fraction of a percentage point. At age 70 and above, it goes up to 1 in 5 people, 1 in 6 people. So it's really, the main risk is for the older people, which is the population of presidential candidates at the moment. But so if you have 1 dead person, 3 weeks ago that person was infected, and that means there are 100 people that carried the virus, okay, because 1% likelihood. But there is also the time delay. because there is a doubling time every few days, every 5 days, let's say. So that means that there are, at the moment where you see one dead person at one city, it means that there are thousands of people that are infected already at that moment. Because of the time delay, you have to take the time delay into account. So, but this is a subject that must be of great interest to people that do modeling of the spread of diseases, because they now can get a lot of data. The main issue is the measurement error, because there were no kits to test people for a long time. So there is even an op-ed in today's New York Times about of a woman saying that for a week, she was sick and her kids were sick, and she demanded tests, and then the government partnered with private sector companies to release enough kits. So this week there are enough test kits, but until now she wasn't able to test. So there must be a large number of people that had symptoms but could not be tested.
Well,
so we don't know.
Maybe they can just anchor the measurements on the percentage dead. I mean, you can up to the quantum effects. You know, Schrodinger's cat. It's pretty.
No, but you don't know what the cause of the standard flu already also has a mortality rate, and it's 10 times more abundant. So then you have to separate the cases. Without testing, you can't tell what is. Anyway, the bottom line is that Harvard, for the first time in recorded history, is doing this, because last time was in '78. It was closed for 3 days, but never beyond that. So this is quite unusual.
What happened in '78?
There was, I was not around. The administrators mentioned it. She said that there was some disease or something. I'm not sure. But it was only 3 days. And now, you know, imagine all these parents that pay $80,000 for their kids to come to school, and now they will have their kids back at home after paying them. I mean, you know, it's a significant crisis, so to speak. And all the people that have to finish PhD, defend it, there are lots of complications. There are kids that have nowhere to, like undergrads that have nowhere to go, you know, because they didn't plan on that. They planned on being on campus, so, and they don't have the means to support themselves. So lots of issues will come up. The staff, the administrators are asked to stay on campus all the time, but the postdocs and the faculty can work remotely. And the plan is to deliver all the courses online using Zoom. So that's the current status, and therefore we will have our future BHI colloquia on Zoom. So as long as a small group of people assembles, that's fine, but we just don't want, I mean, it's very likely that the virus is already on campus. And you don't want to invite speakers here because they might get, on the fly, they might get it. So to protect them, we want only local speakers. So these are the new rules of the day. But as I said, the silver lining is that by May, it's likely to end. Who would like to introduce our speaker today?
Okay, I'll do it.
Okay, go ahead, Alex.
So it's our pleasure to have Mina Himwich, to our last BHI colloquium of the semester, maybe, will tell us about polarization in the photon ring of black holes.
Okay, hi, I'm Mina. Thanks for coming today, given the circumstances. So I'm going to be talking about the universal polarization pattern of the black hole's photon ring, and also the polarimetric signatures that we can see in interferometry. And this is going to be a whiteboard talk with some figures on the screen. It's based on work that is in a paper that came out with Michael and Andy and Alex earlier in January. I have the archive number. So if you want details, it's all in here. And it's a follow-up to a paper that appeared last summer that Alex described in an earlier colloquium. Which is this archive number. Okay, so the goal of both of these papers was to ask, we have this nice image that we observed, and we want to understand better what we're seeing and also what we will see when we go to higher resolution. And understanding that will help us make possibly precision tests of GR in the strong field regime, and also to measure black hole parameters like spin. So what we understood from the paper from last summer was that in the image's intensity, there's a universal series of subrings that are exponentially demagnified copies of the main emission. And this series of subrings is completely determined by GR and universal and independent of the details of what that direct emission actually is. So since we take polarimetric data in addition to data of the total intensity, it's an obvious question to ask, is there a similar universal structure to polarization? And the answer is yes. So the first part of my talk will be explaining what this universal polarization pattern is. And it's essentially a particular rotation, self-similar rotation of polarization ticks between successive subrings. And in the second part of my talk, I'll explain how this polarization pattern, this rotation of the polarization ticks, actually encodes the black hole spin. Sorry, I should have wrote this all earlier. And then lastly, I'll describe how we can use the LBI to measure the spin using a sparse interferometric array. Okay, so the first part of the talk will be describing this universal polarization pattern, and to do that I'll have to review some facts about polarization in Kerr. So in any space-time, the polarization is described by a trajectory p mu that's determined by the geodesic equation. And we can describe the polarization, this is as a vector f mu, this is linear polarization, which obeys f dot p equals 0, and also that f is parallel transported along the trajectory of a photon.
Are you ignoring the circular polarization?
The circular polarization, we're just considering linear polarization now. And circular polarization is like the helicity, and so it doesn't get changed as it's transported along the photon's trajectory. So we'll just be looking at linear polarization. So this is like Q and U. Yeah. Right. So when we specialize to Kerr, the symmetries of the Kerr metric of stationarity and axisymmetry mean that there's a conserved energy and angular momentum along the axis of axisymmetry on the photon's trajectory, which we call E and L. And it's also a special property of the Kerr spacetime that it possesses this killing tensor, which is like a higher form version of a killing vector. Yeah, in Chandrasekhar's book, it's one of the things that he describes as giving Kerr an aura of the miraculous. And it's very special that this killing tensor exists. But from it, you can construct another conserved quantity Q called the Carter constant by contracting it. It's killing tensor of P. And so if you're given these conserved quantities E, L, and Q and an initial position of the photon, so the initial position E, L, and Q, and also some signs specifying the initial direction of radial and polar motion. This will completely specify the photon's trajectory.
So the killing tensor gives you just one conserved quantity, just like a killing vector would.
Yeah.
Okay.
Yeah, and it's the same proof as how it works. Yeah. So for the same reason that this killing tensor exists in Kerr, there's also another special constant called the Penrose-Walker constant, which is usually denoted kappa. And it's constructed, first of all, it's complex, and it's also constructed out of these F mu and P mu. And it's a theorem that this is conserved along the photon's trajectory. So, yeah, if you have this Penrose-Walker constant, which is constant on a trajectory, and you have the momentum at any point on the trajectory, you can solve directly for F. So there are two comments I wanted to make about this Penrose-Walker constant, which is very special. The first is that on a null geodesic, the energy doesn't actually change the shape of the way the photon moves through space-time. So energy is like frequency, frequency is like color. We expect that red and blue photons aren't bent differently by the geometry. So this energy kind of washes out in describing the actual shape of the geodesic.
But that's true in vacuum. If you have a plasma, that's not true.
Right, so we're considering just
Vacuum.
gravity right now, yeah. Just, right, so the energy becomes something that's not really important for the geodesic shape, and the Penrose-Walker constant is what sort of takes the place of energy as an important constant on the photon trajectory. The second comment is that the existence of this Penrose-Walker constant is extremely powerful and constraining. And usually if you want to find the polarization F on a photon trajectory, you'll have to integrate it along the geodesic as it's parallel transported. But if you have the Penrose-Walker constant, and you know P, the momentum at any point on the trajectory, you can just solve directly for F. And so to illustrate how powerful this is, we can ask, how do we find a polarization on the screen for an observer with a black hole? So just recall that there are these coordinates, alpha and beta, where beta is aligned with the spin axis on the observer screen. And using the Penrose-Walker constant, if we're given a point on the screen, alpha beta, which also tells us the momentum with which the photon is reaching us at that point, we can solve directly for F on the screen. So this has components F alpha, F beta, which are related to like Stokes Q and U. This is just equal to 1 over beta squared plus mu squared, where I'm defining mu is equal to negative A plus negative alpha plus A sine of beta observer times beta kappa 2 minus mu kappa 1, beta kappa 1 plus mu kappa 2. So yeah, just to emphasize how powerful this is, if you just are given a point on the screen, alpha and beta, and kappa, you can solve directly for F. And so this is a very special thing, and the existence of the Penrose-Walker constant is what ultimately underlies the universal polarization pattern that I'll describe there. Okay, so switch slides. So yeah, now to talk more about how the polarization looks on the screen. I'm going to describe this sequence of subrings that also appears in the polarization, which is called the Photon Ring. And in Kerr, so because everyone can try and look at the slide, in Kerr there are certain orbits, certain radii at which bound photon orbits can exist. And these consist at a certain range, in a certain range of radii. And if we ask, what are the points on the observer screen from which when you shoot back a light ray, it will get bound at one of these radii, the set of such points forms a curve called the critical curve. And it's parametrized by the different radii at which you can be bound. So because orbits that are slightly unbound either orbit many times and escape to infinity, or they orbit and then eventually fall into the black hole, this critical curve delineates the orbits that we can observe from the ones that we can't, and so it defines the edge of the black hole shadow. So when we look at the observer's screen, we can organize the image into like the number of orbits that, or half orbits n, that a photon undergoes. So in this picture on the left, n is labeling the number of half orbits. And as Alex described in an earlier talk, as you take points that are closer and closer on the screen to the critical curve, the number of orbits that a geodesic shot back from that point executes will diverge logarithmically. And so that means that when you're looking at a ray that's shot back into the matter and picks up photons that orbit between fractional orbit numbers n plus and n minus, if you're looking at a ray that picks up photons that undergo an additional half orbit, they have to be aimed within an exponentially narrow window on the observer screen. So if we have some, similar to that over there, if we have some image of photons that execute n orbits that has a width delta dn on the screen, it will be, the image of photons that undergo n plus 1 orbits will be exponentially demagnified by this factor e to the negative gamma, where gamma is the up and up exponent, again, Alex discussed this before, and it characterizes the instability of the bound orbits. So, right. So that will give us this, if we have some image with delta D on the screen, it'll give us this exponential series of demagnified subrings, and that's what's happening here. This is like a zoomed in picture of this ring, and these lines are the subrings that exponentially approach the critical curve. So, yeah, what this means for the momentum of the photons that reach you is that, so since when you increase n, you're exponentially approaching the critical curve, the photon's momentum, when it reaches you, exponentially in n, approaches the momentum of a photon that's arriving at the critical curve, and we can approximate the photon as just having that momentum. And that means that it's passing through the matter, as you increase n, it's passing through the matter with almost exactly the same momentum. So this is actually a good approximation. The corrections to this approximation are exponentially suppressed in n, and it's actually, those corrections are negligible for n greater than or equal to about 1. So it actually works even for low n. Right. So the only difference between the different n is the sign of p parallel of the momentum parallel to the axis of spin for rays that have n plus 1 or n passes through the matter. So this is p theta, or p aligned with the spin axis. If you have a photon that's undergoing, that passes n times through the matter, and one that passes n plus 1 times through, they're going to have different signs of p theta. So p theta flips sign between the different subrings. So it's actually the only momenta that are related by 2 half orbits or 1 full orbit that are exactly the same. And since those ones pass through the matter with exactly the same inclination, they take up the same Stokes parameters. And if we define a vector S, which is I, Q, U, and D, we find that the Stokes parameters for the n plus 2 ring are equal to those for the nth ring, except for the ones at the n for the n plus 2 ring are appearing at demagnified distance, dn plus 2, whereas the nth ring appears at dn. And this is the same. This is also true for the polarization vector f. So we find that the polarization for subrings that are spaced by 2 half orbits or a full orbit apart have the same polarization, and that's these purple and green ticks that you see on the screen. So, yes.
I'm a little worried about the fact that a millimeter wavelength that we are talking about here for the observations is just short of the wavelength where the region becomes transparent. Before that, at longer wavelengths, it's actually opaque. And therefore, that means that the medium itself has significant effect on the propagation of light at those frequencies. So if you pass the same photon again and again through the medium, get a doubling or a tripling of the effect of the medium.
Yeah.
And I'm just worried that this will wash out. So for example, there is Faraday rotation.
Right.
There is absorption.
Yeah.
All kinds of effects related to the plasma that are not accounted for in these conservation laws.
Yeah. So we, haven't included those. One thing that I will mention is like Faraday rotation is a chromatic effect, and this is achromatic. So one thing we could do is actually use the frequency-dependent violation of this relation that we found to estimate what the Faraday rotation actually is, and maybe subtract it out. I thought we thought about some of these things, but right now I'm just presenting purely.
So just GR.
Yeah, just GR. Yeah.
One surprising thing is if you look at the numerical simulations, we actually see to like the n=6 subring. So it's actually at 230 gigahertz, even the optical depth, at least for some of the simulated models, is quite low.
And what about Faraday rotation?
It's a big deal, but this is a way of, usually Faraday rotation is a mess, right? You get sort of one qualitative number to describe a very complicated system. Here you can isolate the Faraday rotation through the chromatic effect, so you know exactly the plasma properties in the photon shell. It's an amazing opportunity. Yeah, exactly as Mina said.
And one more comment, this is also a theory that tells you when it breaks down, because it gives you many, many, many consistency relations, some from which you can expect spin, but others, which just say this has to equal that. And so if you find a violation of that, then you know that you're not in the regime that's well approximated by vacuum, but you'll know.
Yeah. Okay. So we see this rotation in the polarization between subrings that are separated by two half orbits. And in the case of the intensity, the total intensity, it's emitted in all directions, so this sign of p theta doesn't matter. And you can just go ahead and say directly that the intensity of the n+2 ring is equal to the intensity, of the n+1 ring is equal to the intensity of the n ring. And in the case of polarization, this isn't possible because it's a directed emission. The polarization could depend on things like the magnetic field around the black hole. So in general, we can't relate anything besides the n and the n+2 ring. But it is possible to relate them if we make the assumption that the matter is reflection symmetric about the equatorial plane. Equatorial reflection symmetry, along with axisymmetry and stationarity, is the symmetry of the Kerr metric. And also, we've seen that realistic matter distributions seem to obey the symmetry under time averaging, which also gives us the axisymmetry of the matter. So I think it's a reasonable symmetry to consider. And under this assumption, if we look at this picture, whenever you have a photon that's loaded onto an array that executes n turns at an angle theta, you'll have a corresponding one that's loaded with the opposite sign of p theta and the opposite sign of f at pi minus theta. And so it turns out that under this transformation of theta goes to pi minus theta, negative p, and negative p goes to negative p and negative f, this Penrose-Walker constant gets complex conjugated. And so if you integrate the contribution of these rays over the entire emission region, you'll find that kappa of the Penrose-Walker constant of the n+1 ray is equal to the complex conjugate of the Penrose-Walker constant of the nth ray. And this is the analogous relation for the polarization to what they found for the intensity in the previous paper. So, this tells us that if we know, recall that this formula for f includes kappa. So if you know kappa on the different subrings, you know what f, the polarization vector, looks like on the screen. And if you know the polarization vector for the direct image, or kappa for the direct image, this complex conjugation of kappa will tell you what the polarization is for all of the successive subrings, and that's the universal feature of GR that we're talking about in this paper. So, this is the universal polarization pattern, and now I'm going to talk about how it can be used to measure spin. It's actually pretty immediate to see that from the formula. So if we take sums and differences of the polarization of the nth and n+1 subring, which I'll call f plus minus, And then, yes.
So these could be like the blue and green, the purple
Right,
and green
right,
type.
yes, this is like the blue and the green arrows. So, yeah, if we take sums and differences of them, and then we take ratios of the components of these sums and differences, so like f plus alpha over f plus beta, or f minus beta over f minus alpha, we can eliminate the kappa dependence and just get an equation involving the positions on the screen and polarization ticks. So this tells us that if we know a location on the critical curve, alpha tilde beta tilde, which is, we know it, and we know the polarization of two successive subrings, we can directly solve for the spin. And this is how the spin is encoded in the rotation of the polarization.
Is it simply
ticks.
because at each orbit the photon gains a little bit of a tilt to its or the orientation of the spin?
Well, it's basically because of this thing of p theta flipping sign, of the momentum of a photon parallel to the spin axis when it has n orbits, like it goes up, and if it executes another half orbit, it'll go down first and then up. So the difference in the photons that are coming into the n plus 1th ring causes this rotation. Yeah.
Another way to say it is we don't know what the green ticks are, and we don't know what the purple ticks are, because that depends on the actual emission. But the flip between them, how much the polarization rotates, is just a function of the path through the geometry, which is the same as you go from from subring to subring. And so that's just an effect of the geometry and the spin.
Yeah.
What is this theta? Theta naught?
Oh, that's the observing angle.
Observer angle.
Yeah, yeah, which we assume can be measured in some other way. Yeah, yeah.
Does that mean there's an angle at which you can't tell what the spin is?
Yeah, zero.
Yeah.
If you're looking down the axis.
So you could never tell what the spin was?
I think there are other
Well, there-
equations. It's like,
Just in general, there are other equations?
yeah, because alpha and beta are not defined. So
Yeah.
you could write a different relation, but it's,
Yeah.
Also, the orbital time depends on the spin. So if you have a hot something changing, the time it takes to move around depends on the spin.
Yeah, but these coordinates degenerate if you're looking at face-on, because beta is supposed to be aligned to
Down
the
the spin
axis.
axis.
Yeah, so we need to,
I see.
this situation is actually not adapted to that.
And there's also, you can also look at the shape of the shadow too. If you had infinite resolution, it could be
Yeah.
The Doppler effect is different.
yeah, so there'd be a number of different ways that should all give you the same answer, which is kind of interesting.
Yeah, yeah, exactly. Okay, great. So this is how we see the spin in the polarization, and now I want to talk about how we can potentially measure it in VLBI. So, yeah. As the only speaker, but I'm so I'll just briefly say what's happening with VLBI. So what's measured by the interferometer is this combination of the Stokes parameters, Q plus IU, which we call P. And the interferometer measures the Fourier transform of P. So we can show using this relation of kappa being complex conjugated that when we write P, which Q and U are some known function of kappa, that this relation is true beta tilde plus I U tilde squared P of the n plus 1 subring complex conjugated is equal to beta tilde minus I nu tilde squared P of the nth ring. And nu tilde is just this critical value of alpha tilde plus B sine beta. So this is an equation that involves A, and if you write out the Fourier coefficients of Pn plus 1 and Pn, it gives you a relation between the Fourier coefficients of P, which you can just solve for A. So this is the first of two of our relations for spin. Which involves the Fourier coefficients of P. And the formula isn't like really illuminating to write down, so you can, but it's in the paper and everything's explained there. So it actually, and it involves only 6 Fourier coefficients actually, 3 for each, 3 for one odd subring and 1 even subring. And then the second way actually involves measurement only at a single baseline angle. So here we can look at, this is a plot of the polarized visibility amplitude, or the Fourier transform of the polarization P at a single baseline angle as a function of baseline length. So if we just remember, the Fourier transform of a ring is a Bessel function which can be approximated at long baselines as this damped ringing with ringing coefficients p plus minus. And the difference between the coefficients p plus minus for odd and even subrings encodes the spin. And so we found a relation that just by looking at p plus minus for one odd and one even subring, we can get a relation for the spin. And this actually doesn't involve any absolute phase information.
So on that figure, what are the colors again? You've got green, black, and red.
Yeah, black is the sum, and the red is just the image of the Fourier transform of the polarization of the n equals 2 subring. So yeah, the red is the n equals 2 subring, green is the n equals 1 subring, and this is regions in which the signal is dominated by the n equals 1 subring versus the n equals 2 subring, etc.
But I thought you need to go to very large, long baseline, right?
Yeah.
So, but the
These are
green.
log.
Yeah, so I guess there's
Sorry,
a plot.
what is log?
This is log.
It
300
usually gets to about
gigolambda.
10.
Oh, it's log. It's
Long, it's long. You're saying
Oh,
long,
no.
not
No,
log.
I thought in your paper that
Yeah.
it was extended to much larger values.
It
There's
usually
a-
gets to about 10 gigolambda.
10.
So Mina's, you'll get to n equals 1 if we triple.
No, but for space.
Yeah, just this
Oh.
is a plot from the other paper.
Yeah, exactly. For
Yeah.
space. you
Yeah,
go-
so we'll need much longer baselines
exactly.
to see this signal, but we're trying to make, think about what we would see if we had potentially infinite resolution, or at least higher resolution. But it's possible that we only need one odd subring and one even subring. So once we get n equals 1 and 2, which is hopefully possible, then we can observe this, which is great. Okay, so I'm just gonna probably end here.
Now, both of
Okay.
these methods require knowledge of theta.
Yes, yeah.
Okay.
Well, it's a degeneracy. They just measure this projection. So the question, I guess, is what Ramesh is asking: can you separate sine theta from A somehow?
A sine theta always appears in that combination.
In the
Yeah, yeah. But we're right. So you need to know theta from some other method. Okay. Yeah. So I think I'm just going to stop. And to summarize, we've just gone through how there's a universal polarization pattern of these subrings that have this alternating polarization, and the way that they alternate encodes a black hole spin, and we can measure the spin on a sparse interferometric array with only a few Fourier coefficients, or only using potentially, this is all potential, using a single baseline angle. So, thank you. Okay, yes.
Astrophysics is usually not that elegant in the sense that there are many complicating factors. I'm just running through them to see if any of them introduces an issue. And one of them is the fact that the emission is originating from a plasma that is turbulent and time dependent. So it's not clear that you will maintain a feature over an orbital time.
Yeah.
Or over the light crossing time even, I'm not sure. So the question is, suppose you have time variability. Perhaps the way to recover still the relations that you're talking about is from cross-correlation, but cross-correlation with the time delay, the appropriate time delay. The question is, have you thought about it?
Yeah. I think we're assuming that everything right now can be time average, but that would definitely be a
Oh, but if it's
possible way to-
fluctuating randomly,
Right.
would you still maintain a signal?
I think we would, yeah.
Yeah.
Even though there is a time delay, every ring has more time, every pass. every time the photon goes around, there is more of a time delay, and therefore the plasma conditions change.
So the fluctuations we see in M87 in intensity are very small, right, over many M. I don't think there's evidence that the turbulence is sort of order unity fluctuations in polarization angle or Faraday depth or anything, or the time scales of a single pass through the photon shell. I think you're also kind of referring to the possibility of doing some coherent search for a time delay. We're talking about sort of an incoherent average in time. And that's, you should talk to Shep. He's excited about that.
Yeah, that's, I think we've been thinking a little bit about correlating multiple orbits, which would be very interesting here. I mean, for the polarization, but also for the total intensity for the paper number 1.
So, but in terms of a procedure, you could just sit at a baseline and just average your signal over long time periods, at least if, and that's kind of the freebie. And then there are more exotic possibilities that might also give you new information. But there are certainly easy ways of achieving this time average because the Fourier transform is linear. So averaging in the visibility domain is the same as averaging in the image.
But what, following up on an obvious point, what is the ratio of flux density? Because it seems like it's getting small pretty rapidly. So by the time you get to n equals 3, for example,
Yeah.
what is the ratio of the polarized flux in n equals 3 to the polarized flux in n equals 1?
So the flux, in the intensity, there's a flux ratio. The U and V contributions are signed, so you can't like relate exactly what the total, like.
Well,
So
you
this-
take the total polarized intensity, right? So
Yeah, I guess
Q
you can
plus
take the
I U times the
magnitude
conjugate.
of it. Yeah, I guess you have to look at that in the image space, not in the Fourier space, right? But the flux, yeah, it has the same
Well, the
property of like,
interferometer- The interferometer
Flux
measures
dies
in the
off.
Fourier space, so you look at
yeah,
the cross correlation amplitude between right and left, for example.
yeah. I mean, I think it exhibits the same pattern of the flux dies off as you increase.
And
Yeah,
Right, it's going to be e to the minus gamma, just like for the intensity.
it'll be minus 2 gamma, 3
Exactly.
gamma,
So
4
the catch that Mina is referring to is that, right, as you jump across 2 subrings, you get e to the minus 2 gamma. As you jump from one subring to the next, we can't it's not as clean.
Yeah.
I see.
So jumping 2 subrings gets you 2 factors of e to the minus
And
gamma.
how large is gamma?
10% for a rapidly spinning black hole. E to the minus gamma is 10%.
10%. So you lose a factor of 10.
Yeah.
yes.
How many viable targets do you envision for this method?
Currently M87.
Thinking
You
about a
can ask
space
Shep,
station.
I guess.
Well, you could go, I mean, if you had, well, I mean, Michael's been talking about L2, so that gets you out to 80 to 100 to 200 gigalambda. And at that point, a number of things might come into range. But if you really need to distinguish between these rings, then there's only like a few, yeah.
But then the variability timescale of those other sources would
Well, I'm assuming they're terahertz.
By the way, sine theta for M87 is known, isn't it?
Yes, but I would like to measure it properly using the EHT.
But it would be nice to see that it aligns with, so if you get A of 1 for the sine theta of the jet, then it's a good one.
Well, so I think polarization only tells you a sine theta, but at this point, there are just so many relations on these subrings. If you look at intensity, you can get to A and not a sine theta. So I think if you can see these subrings, it's like, there's just every month there are new relations that we discover. So it's so over-constrained that you should be able to.
Yeah,
So
if you
we-
can disentangle theta from A, I think that will be really valuable. We have this astrophysical estimate of theta, but this is beautiful physics measurement. So I would put a lot of trust in something like this if it can be done.
Great, yeah.
Yeah.
fast.
Okay, I'm also happy to talk more anytime about this. So, yeah, thanks again.
Excellent.
Okay, that's-